We are talking about a legend, a machine whose very existence has defied every notion of speed and altitude. This is the SR-71 Blackbird, a masterpiece of engineering in aviation history. And if you're someone who craves the extraordinary stories behind extraordinary machines, today, let's explore the SR-71 Blackbird together. Known as a long-range aircraft capable of flying at altitudes of up to 16 miles, the SR-71 not only allowed pilots to see the curvature of the Earth, but also the dark expanse of space surrounding them. The birth of the Lockheed SR-71 Blackbird marked a shining milestone in US aviation history. Developed in absolute secrecy, this reconnaissance aircraft had the capability to fly at supersonic speeds near the edge of space, far beyond the reach of any missile of its time. The origins of the Blackbird stem from the United States' urgent need to gather intelligence on the Soviet Union. A US Air Force report highlighted a concerning reality. To evade the Soviet Union's increasingly sophisticated air defense systems, reconnaissance aircraft would need to operate at an altitude of at least 70,000 feet, far beyond the capabilities of existing planes. Previously, the CIA had relied on the U-2 Dragon Lady to conduct high-risk surveillance missions over Soviet airspace. However, when the Soviet Union shot down a U-2 piloted by Francis Gary Powers in 1960, it served as a wake-up call, greatly accelerating the push for a reconnaissance aircraft with superior speed and better evasive capabilities against enemy air defenses. The incident immediately triggered serious diplomatic consequences amid the escalating Cold War, further reinforcing the urgent need for a new reconnaissance aircraft that could fly faster, higher, and safer against anti-aircraft threats. According to aviation historian Peter Merlin, the CIA wanted an aircraft that could fly above 90,000 feet at high speed while remaining invisible to radar, as they believed such technology was entirely feasible at the time. Through relentless efforts, the A-12, Blackbird's predecessor, was born. Following that, the SR-71 Blackbird was designed to achieve speeds exceeding Mach 3, or 3 times the speed of sound. The jet black exterior, designed for heat dissipation and earning the nickname Blackbird, combined with the sleek lines of its elongated fuselage, made the SR-71 look like nothing that had ever come before, a design whose striking beauty has remained timeless. The SR-71 was uniquely designed entirely around its engine system, which can be considered a technological marvel. The Pratt & Whitney J58 turbojet engine was an integral part of its success. Have you ever wondered how an aircraft could sustain a speed of Mach 3.2 for extended periods without experiencing severe engine or fuel issues? To achieve this, the SR-71 did not rely solely on a conventional turbojet engine, but incorporated a sophisticated system that enabled it to transition from a turbojet to a ramjet during flight. This system, known as the Airflow Management System, featured a powerful regulation mechanism that ensured a seamless transition between turbojet and ramjet operation. A 26-inch-long inlet spike could move up and down to regulate airflow and maintain the shockwave in an optimal position. This was crucial because without optimization, energy would be lost through friction, reducing engine efficiency. The use of an adjustable inlet spike not only allowed the SR-71 to fly at incredible speeds, but also ensured efficiency throughout its entire flight. In the design of the SR-71, an air channel was created to direct airflow from the inlet spike through the J58 engine. This airflow was then used to cool the engine, enhancing efficiency and allowing the aircraft to fly even faster. As the air passed through the engine, it re-entered the airflow after the compressor, providing additional thrust by introducing more oxygen into the combustion process and increasing pressure through the nozzle. The air entered this system through several specialized mechanisms, including a shock trap, also known as a protective vane, that minimized the formation of the boundary layer, which consisted of slow-moving air. The intake system at the front and rear of the engine played a crucial role in regulating the pressure of the inlet airflow, ensuring stable operation. This system not only cooled the engine, but also controlled shock waves within the intake airflow. If the pressure became too high, pressure sensors would activate the front air intake doors, allowing excess pressure to escape and preventing an engine stall, commonly referred to as an unstart. In such situations, the front intake doors would fully open, and the inlet spike would move forward to relieve pressure and reposition the shockwave into an optimal location. Interestingly, beyond the intake system, the SR-71 also had 6 bypass ducts that routed compressed air directly from the compressor to the afterburner. This was the primary mechanism that enabled the transition from turbojet to ramjet operation. While afterburners were not fuel efficient, they became incredibly effective as the aircraft's speed increased. Notably, engineers could have extracted even more thrust from the engine, potentially increasing the SR-71's maximum speed to Mach 5. However, they chose to limit it to Mach 3.2. Why? One crucial factor was fuel efficiency. Although fuel cost was not a major concern for a military aircraft, carrying extra fuel increased the plane's overall weight, which in turn led to higher fuel consumption. This was a trade-off that engineers had to carefully calculate. Another key factor is that the SR-71 was primarily designed for reconnaissance missions, not combat. As a result, its internal space was not allocated for weapons, but instead dedicated to fuel storage. Thanks to its smart design, this aircraft could carry an impressive amount of fuel. Despite having a specialized design to prevent fuel leaks, the SR-71 still leaked fuel while taxiing on the runway. This was due to the gaps in its titanium airframe, which were intentionally designed to expand and contract during flight. However, this was not a flaw, but rather a characteristic of titanium as a material. Engineers implemented a total wet-wing fuel tank system, where the fuel was not stored in separate fuel bladders, but instead within the aircraft's airframe itself. By reapplying a sealing compound after each flight, the SR-71 consistently maintained operational efficiency. Despite its fuel leakage, the total amount of fuel the SR-71 could carry was remarkable. When fully loaded, the aircraft could carry between 61 to 63 tons of fuel, accounting for about 59% of its total weight. This was a critical factor in sustaining the fuel-hungry engines of the SR-71 and enabling it to maintain Mach 3.2 for extended periods without major fuel issues. Even without aerial refueling, the SR-71's operational range was quite limited compared to other long-range reconnaissance aircraft. Its range varied significantly, as higher ambient temperatures reduced engine efficiency. A fully loaded SR-71 could consume nearly 13 tons of fuel when accelerating from Mach 1.25 at 30,000 feet to Mach 3 at 078 degrees Celsius, 70,000 feet. If the ambient temperature was 10 degrees Celsius above standard, fuel consumption could rise to 36% of the total fuel capacity. Conversely, if the temperature was 10 degrees Celsius below standard, fuel consumption dropped to just 7.2 tons. Naturally, the aircraft's range depended heavily on speed and afterburner usage. On average, the SR-71 could fly about 5,200 kilometers, enough for a one-way trip from New York to London. But this was not ideal for reconnaissance missions where landing in the target area was not an option due to enemy detection risks. However, with aerial refueling, the SR-71 could theoretically fly indefinitely as long as no technical issues arose. Its actual range was entirely dependent on the pilot. The longest SR-71 mission in history took place in 1987, when the US military deployed the aircraft from Okinawa to observe the Iran-Iraq War. The flight lasted 11.2 hours and required at least 5 aerial refuelings. So, if fuel and engine power were not the limiting factors for the SR-71's top speed, what was? At Mach 3.2, the SR-71's nose reached 300 degrees Celsius, while the engine nacelles could reach 306 degrees Celsius at the front and 649 degrees Celsius at the rear. This was the true limiting factor for its maximum speed. Without careful material selection and design, the aircraft would simply overheat and fail. Even the fuel itself had to be specially formulated to handle this extreme heat. This fuel, known as JP7, had a very low volatility and a high flash point. This was essential because the fuel would leak on the runway, and engineers needed a non-volatile, non-flammable fuel to prevent fire hazards and protect ground personnel from toxic fumes. Interestingly, JP7 was not just used as fuel, but also as a coolant for the entire aircraft. The fuel was pumped through the aircraft's frame to cool critical components such as engine oil, the hydraulic system, and electronic control systems. When the fuel became too hot, it was sent directly to the engines for combustion. However, because JP7 was highly stable, the aircraft required a special chemical called triethylborane (TEB) to ignite the fuel in the engines and afterburners. Pilots carried only about 16 shots of TEB, so they had to manage them carefully, especially when slowing down for refueling and managing engine restarts. One major question I had about the SR-71 was, why was it painted black? Commercial aircraft are usually painted white to reflect heat and prevent overheating, so why was the SR-71 black? Earlier versions of the SR-71 were unpainted to save weight, and only the hottest sections were coated in black paint. But did the black color truly absorb more heat? You might know that the Concorde was once painted blue for a Pepsi advertisement, and it had to reduce its speed due to excessive heat absorption from the sun. However, the Concorde didn't fly as high or as fast as the SR-71. At higher altitudes, solar radiation absorption becomes less significant compared to the heat generated by aerodynamic friction. To understand this, we must consider Kirchhoff's law of thermal radiation, which states that a good absorber of heat, such as a black object, is also an efficient emitter of heat. Therefore, painting the SR-71 black actually helped it dissipate heat more efficiently, preventing the aircraft from overheating. Of course, it's not just the paint that helps the SR-71 manage its temperature. The materials used in its construction also need to be extremely stable at high temperatures. Aluminum, the material commonly used by aerospace engineers, such as in the Concorde, is inexpensive and easy to work with, but it has limitations in heat resistance. In contrast, titanium, which makes up 93% of the SR-71 structure, has an excellent strength-to-weight ratio, but is extremely expensive. Although titanium is the seventh most abundant metal in the Earth's crust, its refining process is time-consuming and requires costly consumable materials. Despite its strength and excellent heat resistance, titanium is difficult to work with. When welded or forged, it reacts easily with air, making it brittle and prone to breaking. For this reason, titanium is rarely used in structural components of aircraft. However, titanium's true advantage lies in its ability to withstand extremely high temperatures. The reason for this is complex and will be explored in more detail in future articles, but in general, titanium alloys have a very strong crystal structure that helps prevent degradation when exposed to heat. Titanium alloys can withstand temperatures up to 600 degrees Celsius before the atoms in their structure begin to slip and disperse, allowing titanium to retain most of its strength even when exposed to 300 degrees Celsius. Moreover, titanium has a very low thermal expansion coefficient, which helps minimize the expansion and contraction we discussed earlier, thereby reducing thermal stress in the aircraft structure. However, titanium still has its limits. For the SR-71, this limit was around Mach 3.2. Today, engineers have made significant advances in materials science. The SR-71 incorporated heat-resistant composite materials, particularly radar-absorbing panels, which were placed within the aircraft's structural framework in key locations. However, at the time, the manufacturing techniques required to produce load-bearing composite materials did not yet exist, but that has since changed. What do you think about the combination of advanced technology and military strategy in the design of the SR-71? Could future developments in aerospace technology bring similar improvements, or even surpass current limitations? Share your thoughts with Power Insider. Although satellite reconnaissance (UAVs) and long-range hypersonic missiles have made remarkable progress in recent years, the US Air Force still seems to dream of a versatile Hero, an aircraft capable of high-speed reconnaissance, ready to take on missions that other platforms struggle to fulfill. Previous reports suggest that Lockheed Martin's Skunk Works division may have developed a new reconnaissance aircraft for the US Air Force. This has sparked speculation about a worthy successor to the legendary SR-71 Blackbird. The SR-72, dubbed the Son of Blackbird, is expected to be the next hypersonic iteration of the SR-71 Blackbird, which still holds the record as the fastest manned aircraft ever built. This new aircraft is also being developed by Lockheed Martin's Skunk Works. During its operational lifetime, the SR-71 famously evaded more than 4,000 missile attacks. The goal for the SR-72 is to replicate this impressive feat. However, the Son of Blackbird is expected to be even faster than its predecessor, allowing it to outrun the most advanced air defense systems today. To achieve this, the new aircraft must reach hypersonic speeds above Mach 5.0, an almost unimaginable capability. According to the science magazine Popular Mechanics, vehicles traveling between Mach 1 and below Mach 5 are classified as supersonic, while those reaching Mach 5 and beyond are designated as hypersonic. Since 2007, rumors about the SR-72 have circulated. Several sources suggest that Lockheed Martin is developing an aircraft capable of flying at 6 times the speed of sound, Mach 6, twice as fast as the SR-71. At such speeds, the aircraft could evade even the most sophisticated air defense systems, including the S-400 and S-500 missile defense systems. Operating at altitudes far beyond those of current fighter jets, this platform could potentially launch hypersonic missiles with extreme speed and precision, enabling rapid strikes on targets. Reportedly, the preliminary design of the aircraft features a large delta wing along with 2 engines mounted beneath the wings. This shape is believed to optimize aerodynamic performance at hypersonic speeds, but may also affect the aircraft's maneuverability at lower speeds. Despite its advanced design, the development of the SR-72 still faces numerous challenges, particularly in terms of materials capable of withstanding its extreme speeds. Additionally, concerns remain regarding scalability and sustainability, as the cost of developing hypersonic technology is extraordinarily high. To achieve hypersonic flight capability, Lockheed Martin has partnered with Aerojet to develop an entirely new propulsion system for the SR-72. The key focus is the application of scramjet, supersonic combustion ramjet technology. While scramjets promise astonishing speeds, they have a fundamental limitation: they only operate efficiently at extremely high supersonic speeds, beyond Mach 5, Mach 2.5. Scramjets function by compressing incoming air at supersonic speeds before igniting the fuel, a highly complex and difficult to control process. As a result, scramjet efficiency drops significantly at lower speeds, creating a major challenge in designing an aircraft capable of stable operation throughout all phases of flight, from takeoff and cruising to landing. To overcome this challenge, engineers devised a groundbreaking solution: the turbine-based combined cycle (TBCC) propulsion system. This system integrates 2 different types of engines: a turbojet, which is efficient at lower speeds, up to around Mach 2.2, and a scramjet, which reaches peak performance at hypersonic speeds, above Mach 2.5. This means that the aircraft will rely on turbojet engines for propulsion until it reaches Mach 3. Once at supersonic speeds, a dual-mode ramjet will take over to power the rest of the flight. The TBCC system allows the SR-72 to seamlessly transition between these 2 types of engines depending on flight conditions. At lower speeds, the turbojet engine takes the lead, and once the aircraft reaches sufficient velocity, the scramjet activates to push it into hypersonic speeds. Another key feature is that both types of engines will share the same air intake and exhaust system, minimizing weight and complexity. However, each engine will have separate airflow pathways to ensure optimal performance. This innovation has caught NASA's attention, leading the agency to support research efforts by awarding Lockheed Martin a $1.13 million contract. It is speculated that the hypersonic SR-72 will have far greater capabilities than its predecessors, the X-43 and X-51 Wave Rider, which were primarily experimental platforms for testing scramjet technology. Unlike those aircraft, the SR-72 is believed to be designed with greater capabilities and will incorporate more advanced materials, such as carbon-carbon composites. These materials can withstand extreme thermal stress more effectively than the titanium shell used for heat dissipation in the SR-71, which was necessary due to the high temperatures generated at high speeds. USNI News explains that one of the biggest challenges for the SR-72 is managing the intense heat caused by skin friction at Mach 6. To cope with thermal stress during continuous high-speed flight, the SR-72 is considering two potential approaches. One is an active cooling system, similar to how space shuttle tiles function, utilizing internal heat channels to circulate coolant, effectively dissipating heat. The second approach focuses on developing and utilizing superior heat-resistant materials, such as advanced titanium alloys or ceramic matrix composites, which can maintain their strength and shape even under extreme temperatures. The final choice will depend on material testing results and a cost-effectiveness evaluation to determine the optimal balance between technical performance and economic feasibility. The SR-72 promises to be more than just a speed machine. It is envisioned as a versatile platform that combines speed, stealth, and operational flexibility. To achieve this, the prototype will likely be equipped with advanced avionics and possibly even artificial intelligence (AI) systems to automate functions and optimize performance, a significant leap beyond previous hypersonic aircraft. One potential application of AI is its ability to automatically adjust flight parameters and onboard systems, optimizing efficiency and reducing the pilot's workload in complex combat scenarios. However, it is worth noting that stealth technology may not be very effective on an aircraft like the SR-72, as radar-absorbing materials may not withstand extreme temperatures. Although its large infrared signature and radar cross-section similar to the SR-71 may limit its stealth capabilities, its hypersonic speed and rapid withdrawal ability will be the key factors ensuring the SR-72's survivability. The ability to quickly exit an area and outrun most sub-hypersonic interceptor missiles will make stealth concerns secondary. The SR-72 is envisioned as a strategic hypersonic reconnaissance UAV, with an unmanned design, reducing risks for pilots during high-speed, high-altitude missions. Notably, it will be equipped with Lockheed Martin's new Hypersonic Strike Weapon, HSSW, a system capable of launching hypersonic weapons at superior speeds, reaching hypersonic velocity almost instantly. The advantage of the HSSW is its ability to remain undetected for longer, combined with the SR-72's extreme speed, leaving adversaries with very little time to react. Officials have also stated that the final production version of the SR-72 will have a similar size to the SR-71, measuring over 30 meters in length with a comparable range, and is expected to enter service around 2030. This timeline aligns with the US Air Force's hypersonic weapons development roadmap, with hypersonic strike weapons developed in 2020 and hypersonic reconnaissance aircraft planned for 2030. However, the future of the SR-72 remains uncertain, dependent on funding decisions from the US government. Ongoing discussions between Lockheed Martin and senior officials will be crucial in determining whether the dream of the son of Blackbird becomes a reality. If given the green light, The SR-72 will not just be a new weapon, but also a symbol of America's technological prowess and innovative capabilities. As tensions between Washington and Beijing continue to rise, the race to achieve next-generation capabilities is accelerating. It will send a clear message to potential adversaries. The United States remains at the forefront of military technology and is willing to invest in bold solutions to protect its national interests. Both the U.S. Air Force and the People's Liberation Army Air Force, PLAAF, are aggressively pursuing their own sixth-generation fighter and bomber programs, emphasizing stealth, automation, and laser weapon integration. The PLAAF is also working on developing its sixth-generation fighter, reportedly codenamed JXX. Although details remain scarce, analyses suggest that the JXX may possess stealth capabilities, advanced sensor systems, and directed energy weapons such as lasers or high-power microwave weapons. Meanwhile, Moscow is also demonstrating its determination to lead in hypersonic weaponry. The Zircon cruise missile, designed to strike both naval and land targets, presents significant challenges for existing defense systems. In addition to Zircon, the Avangard system is another example of Russia's ambitions. Avangard is a hypersonic glide vehicle, HGV, that can be launched from an intercontinental ballistic missile, ICBM, allowing it to maneuver through the atmosphere at extreme speeds. These developments highlight the intensifying military technology race, driving global powers to continuously invest in the most advanced weapons systems. If you're fascinated by these extraordinary machines and the stories behind them, don't forget to hit the like button and subscribe to Power Insider. Let us know in the comments which powerful machine you'd like us to explore next.